Good evening and welcome to the Birch Aquarium at Scripps Institution of Oceanography. My name is Nigella Hilgarth and I'm the Executive Director, and it gives me great pleasure to welcome you to the latest Geoffrey B. Graham Perspectives on Ocean Science lecture series. And it gives me great pleasure this evening to introduce Dr. Tony Haymet to you all. Most of you already know Tony. He is the Director of Scripps Institution of Oceanography, and he's also the Vice Chancellor for Marine Science at UCSD. However, some of you may not know that he's only been with us for 9 months. He came from Australia, where he was the Director of the equivalent of Scripps. And again, some of you may not know that he is an extremely distinguished chemist in his own right. And this evening, he's going to give us a lecture on climate change research at Scripps. Please welcome Dr. Tony Haymet.
Well, good evening, everyone, and welcome. Tonight I'm here as a spokesperson. None of what I'm going to talk about tonight is my own research, but you might treat it as an indirect talk about what's happening at Scripps, and for my many colleagues from Scripps who are here, you might use it as a way to get inside my mind and see what the director is thinking about, at least in the field of climate change. So let me say that tomorrow will be my 9-month anniversary, and it's been a real treat to be here and interact with our wonderful students and faculty, not to mention the administrators, and I'm certainly looking forward to many more such happy months. So what I'm going to talk to you about is what's on my mind in climate change, and this might give you an indication about where we can expect Scripps to be going in the climate change arena in the next couple of years. I imagine I'll run out of time as we get towards the last topic, so we'll talk about ice and glaciers as much as we can. The subtitle of the talk was Feeling the Heat, Following the Heat, because a lot of what we need to understand in climate change in the next couple of years to figure out how we respond to this issue has to do with our oceans and ice, and how heat that we generate as human beings is going to be incorporated into our planetary system. So first things first, here is the definitive climate record. Next April will come up on the 50th anniversary of this great experiment based here at Scripps. The ultimate antidote to skeptics and denialists, the fact that over the last 150 years we've added 1 in every 4 CO2 molecules that we currently find in the atmosphere. Let me say that again. 150 years ago, for every 4 CO2 molecules that we pluck out of the air, there were only 3 in the atmosphere. So by our efforts and our ancestors' efforts, we've managed to take the concentration of CO2 on the planet from about 280 parts per million to past 380 parts per million. I'd say that's quite a good effort. The good news is that CO2 molecules trap heat. If you believe in quantum mechanics, then trust me, you believe in this effect. It's a very simple piece of science. It's an important reason why planet Earth has the temperature that it has. It's why we're warmer than some other planets. The bad news is that CO2 molecules trap heat. And so if 3 of the molecules trap heat, then the other quarter of the molecules equally trap heat. And that's the problem. The problem is that we're trapping more heat than we used to. This curve wasn't delivered to us out of thin air, but by a scientist. Here's Charles David Keeling, who started these measurements almost 50 years ago, perfected the technique for measuring them, convinced some troublesome director that they should be done on the top of a mountain, not off ships or some other crazy director's idea, and persisted with it in the face of adversity and changes from funding agencies and all the rest. And I can't tell you how important this curve is to us in the science community, and I think also in the policy community. And to give you an indication of just how this is regarded in the science community, This is a photograph of a wall in the new National Academy of Science building in Washington, D.C. I'm sure you'll recognize some of these images. Over here we have DNA. Here we have Darwin's finches. We have a few fancy chemical molecules here. This is the entrance to the library. And this looks like the San Francisco Golden Gate Bridge. And here we have the Keeling curve. I'm tempted to say this is the most famous scientific result collected out of California, but I might get challenged by argumentative chemists and physicists and atomic bomb makers and other people. So let me just say that this is truly a result that belongs on this wall. And it's important. And it's not all that difficult. You know, I've summarized for you in a couple of minutes why there is global warming and why we believe we understand the mechanism of global warming. It surely is not rocket science. Here's another curve that's got a little more science in it that you've seen from Scripps scientists like Jeff Severinghaus. And this is the historical record of CO2 concentration in the atmosphere. How do we know this? Well, I don't have time to tell you, but if you step into our climate exhibit immediately after the talk, you can see two completely independent ways by which this record has been established. One from ocean sediments and another from tiny bubbles of gas that have been trapped for 650,000 years in ice cores. What this record shows is that, yes, there have been oscillations in the concentration of CO2 over our planet's history. We have a detailed record that goes back even further than I show here. But in all that recorded time and oscillation of ice ages and interglacial warming periods, the concentration has oscillated between 180 and 280 parts per million. And that Keeling curve, hard won over the last 49 and a half years, compresses nicely into that last little piece. So that's why we're worried. We've pushed this climate system into a place where it does not naturally belong. And because we know quantum mechanics and because we know CO2 molecules absorb heat, we're concerned about our climate. So what's going to happen if we do nothing? What's going to happen if we do nothing, except continue as we are, is that we'll burn all the fossil fuels that are in our planet. And that would be the yellow curve on the upper panel of this graph. So just about every scientist and now almost every policy maker I meet, whether in the US or in Europe or other benighted countries like Australia, they all agree we have to stop somewhere. And because CO2 molecules live for 100 years in our atmosphere, in order to stabilize somewhere, and I've chosen the level of 450 parts per million because I'm an optimist and because I can count, in order to do that, we need actually to not only flatten off, level off our emissions of CO2, but we need to, over the course of the next 15 to 20 years, actually reduce them. Now, what I like to do is set targets, because that's the kind of guy I am. What gets measured gets done, at least around Scripps. There'll be lots of debates, especially after what happened last week in Europe, about whether we should use carrots and sticks and taxes or goals or rely on technology or miracles. Whatever happens, if we're going to look after this planet, we need to find a way of first flattening off our emissions and then rolling them back. These are nice units over here. If you've never thought about what a petagram of carbon per year is, it's a unit that you should try to get your mind around. But since I've been on this planet, as a population, we've gone from emitting 2 petagrams of carbon per year to well over 8, close to 9 petagrams of carbon a year. So we haven't exactly been conservative in the time that I've been around, and it's time for us to change. I'm not the only one who thinks that. So here's a journal that your director reads. Maybe years ago when I first started getting this journal, it was to figure out what those bad guys were thinking, but we all evolve over the years. And so here's not this week's issue, but the issue of the week before, and I urge you to read the 15 pages on climate matters in this journal. And let me read what it said. This is direct lifted from The Economist. A study recently published by America's National Academy of Sciences found that worldwide emissions, which had been growing by 1.1% per year in the 1990s, grew by more than 3% a year between 2000 and 2004. If you want to see more details on this, if you go to the IPCC report, where there's a complete summary of what the Annex 1 countries are doing in response to the Kyoto Protocol. The Annex 1 countries are all the people that signed up for it, but include the countries that ratified it and the two that didn't, the United States and Australia. There's a report for each one of those countries, and you see that there are many European countries that were actually reducing their carbon emissions until about the year 2000, but there are many countries that show a discernible uptick in emissions between the year 2000 and 2004. Going back to what The Economist said, this is faster than the most pessimistic projections of the UN's Intergovernmental Panel on Climate Change, a body set up to make authoritative pronouncements on the science of global warming. I don't know about pronouncements, but what IPCC does, and if you've heard Richard Somerville speak on this, you know firsthand from him what it does. It's a body that doesn't do science, it assesses science. So I'd say its job is to put out an authoritative assessment rather than a pronouncement. But what the rest of the sentence is true, faster than the most pessimistic predictions. It's also faster than economic growth. So when you hear various world leaders say that, oh, we can't possibly reduce our carbon emissions because it's linked to economic productivity, just bear in mind that since 2000 we've been increasing our rate of CO2 production faster than we've been increasing our gross national product. So this is a pretty important issue of The Economist. I think it lays to rest any concerns that people have that policymakers and economists around the developed world are not paying attention to what's going on. I think the question that we all wonder about, especially after next week, is whether we're going to respond quickly enough to the challenges that we understand all too well. Stay tuned. So I'd like to take you through now two things that Scripps is going to be investing more in over the next couple of years. And that investment normally takes the form of hiring more people to help us in this area. So that will happen over time, I think, as our faculty vote and we find the right people. And those two things we're going to do are connected with ocean acidity and with ice and glaciers. So let me take a little time to slowly go through those features. This is a busy slide, so I'm going to take some time to go through it. It's adapted from the second last IPCC, Intergovernmental Panel on Climate Change report. And it really summarizes our planet, and I'd like you to think about it for a way of tracing the heat. Right? So when you're investigating Watergate, you follow the money. When you're investigating climate change, you follow the heat. And that's what we're about tonight. So the biggest reservoir of heat, the part of our planet that can absorb most heat, is in the ocean. The ocean has a much higher heat capacity than the atmosphere. I'll probably get the numbers wrong, but the top few centimeters of the ocean have the same heat capacity as the entire heat capacity of the atmosphere, way out to 10 kilometers and beyond. So if you want to understand where the heat might get absorbed, you have to understand the ocean. And we'll talk a little bit more about what happens to the ocean when it absorbs this heat and when, in fact, it absorbs the CO2 that's been emitted into our atmosphere. The second thing we'll talk about is all the ice on the planet. And that's sometimes collectively called the cryosphere. And that's everything that contains ice. So that would be permafrost and frozen sea, permanent ice, glaciers, snowpack, frozen tundra, the whole thing. Everywhere in the planet where there's water found in its solid form. And so what happens in this view of the Earth's climate system is that molecules are exchanged, matter is exchanged, and energy is exchanged. And to really understand what we've done to the planet and what we're about to do to the planet, we have to understand how matter and energy move around this system. But there's no argument about what the two most important things are. Even though we emit stuff into the atmosphere, the heat and ultimately the matter end up into the ocean and the ice. So we're first going to take a look at ocean. And I have a couple of chemical equations here just to try to prove that I am a chemist, or at least I used to be a chemist. So I'm going to talk to you about the other thing that CO2 does. CO2 doesn't just absorb heat and indirectly trap it in our planet. It actually dissolves in the ocean. And lucky for us, our ocean has a complicated buffer system, so that a lot of the CO2 doesn't show up directly. But we've now emitted so much CO2 into the atmosphere, all of those petatons of carbon every year, that we've actually made a difference to the hydrogen ion concentration in the ocean. Or if you remember a little bit of high school chemistry, the so-called pH of the ocean, and we'll come to that. So in many thousands of years, the ultimate fate of this CO2 is going to come into the ocean, it's going to dissolve into the ocean, and at the very end, the death of the climate change issue, in thousands and thousands of years, it'll end up precipitated as minerals on the bottom of our oceans. Unfortunately, that's not going to happen fast enough to do us any good. So I'm going to talk to you tonight about the intermediate phase, what's going to happen in the next 100, 200, 300 years as that CO2 enters the ocean. What it does is going to change the pH of the ocean. So we don't have as good a measurement of the pH of the ocean. That's an indirect measure of the hydrogen ion concentration minus the logarithm to the base 10 of the hydrogen ion concentration for those of you following along at home. We don't have fantastic records of that. But we have okay records going back 44 million, 55 million years. We have actually at least two different methods to do that. Both of them are imperfect, but they agree very well. And they agree that going back 44 million years, of which I have part of the record here, the pH of the ocean has been around 8.2. But I want to show you tonight some new data that shows that the pH of the ocean, which started long before us as pH 8.2, is no longer. And so this plot, taken from a 2005 paper that's become quite famous, that goes back in time, I think, to the late 70s, says that if we keep emitting CO2 at our current rate, we will make a measurable dent in the ocean pH. This is not just an academic question. I do believe that we've already made a measurable change in the pH, and I'll show you some records that are very analogous to the famous Keeling curve for atmospheric CO2. But very soon we will enter a regime where we haven't seen the planet for 44 million years, and that will have dire consequences for everything that makes a calcite shell. Okay, well, I know you've been waiting to see a few chemical reactions, so here we go. When CO2 dissolves in water, especially in the ocean, it makes H2CO3, which then dissociates into H plus and HCO3 minus, hydrogen carbonate ions. And these hydrogen carbonate ions, the hydrogen ions then react with another CO3 2 minus ion to make more hydrogen carbonate. So the net reaction for you chemical experts are that CO2 dissolves into the ocean, chews up the natural amount of carbonate that's already in the ocean, and makes hydrogen carbonate ions. So this is part of the famous buffer effect. But the net effect is that it reduces the concentration of carbonate ions in the ocean. Why is that important? Well, it's important because everything from corals down to little tiny shell-like objects, pteropods and other things in the ocean, make their living by excreting external shells made out of calcium carbonate. So they're actually little factories that have calcium ions that they're able to incorporate with carbonate, and if they're successful enough to get over what we call the nucleation barrier and make a calcium carbonate shell, they find that the ocean is supersaturated with respect to calcium carbonate. So to put it in a nutshell, we're going to make it very hard, and indeed relatively soon impossible, for organisms that make calcium carbonate shells to make them. And if we go much longer, I think this is really going to hurt. Now you say, well, it's a big ocean out there. How can a few little Homo sapiens actually make a difference? And so I'm proud to show you for the first time an output from the Keeling Ocean CO2 program, given to me by Andrew Dixon, one of our professors in residence, that shows the acidity record, the pH record of the ocean, as a function of time in 3 separate locations, 2 in Bermuda and 1 in Hawaii. Now you'll see that these curves oscillate on an annual basis, just like the Keeling curve does, and if you want to understand more about that, again, the exhibit is open for your entertainment, but it's basically the breathing of the northern hemisphere, the fact that we have most of the land mass in the planet in the north rather than the south, and with the cycle of winters and summers, there's an increase and decrease in the concentration of CO2, and lo and behold, with the right kind of sophisticated chemical measurements, you can see it in the ocean. Now, I was pretty upset when I saw this data, because it never occurred to me that on a period of 15 years I would be able to see with the naked eye a change in the concentration of acidity. But here it is. Where did we start? We think in 1850 the pH of the ocean was much as it had been for the previous 44 million years, and that was a pH around, in these units, with this definition for the chemists in the audience, around 8.19. I think you can see in this graph that the pH is markedly decreasing, no matter which record you look at. And moreover, that without many more decades, the average value of the pH of the ocean in every location, shown here, will exceed the former minimum value from the annual oscillation. Now I know sadly there are a few of you in the audience who aren't professional chemists, and we'll try to rectify that over time, but until then, let me take this data and plot it as the concentration of hydrogen ions. So that's very same data, just plotted as the total hydrogen ion concentration. It's the number of, roughly speaking, H+ ions in the ocean, corrected for something to do with sulfate. But whatever this number is, back in 1850, it was down here at 6.5. And I think everyone would agree that there's a measurable increase in that time series. So again, this is not controversial. This is not some great model. This is not some controversial method of analysis. This is just a very sincere and patient way of analyzing water samples taken correctly from the world's oceans and analyzed for the total hydrogen ion concentration. So we're already, averaging up here something like 8 in these units, famous units of nanomoles per kilogram. In these units, we've increased the hydrogen ion concentration by over 30% in the last 150 years. I'm not trying to scare you, but that's a number that scares me. Just to emphasize what this means, the way that we measure in chemistry the saturation state of the ocean is we look at the concentration of calcium ions, multiply it by the concentration of carbon ions, and divide it by its equilibrium constant. If that number is greater than 1, then the calcium carbonate shells in the ocean are stable. If it's less than 1, calcium carbonate shells are unstable, can in fact dissolve in the ocean, and are basically impossible to make. So here are some of the little organisms that make carbonate shells. Now you may ask me, when are we actually going to reach this period where the oceans are profoundly different? Let me just take a moment to say that I'm not of the view that we'll kill all of the life in the oceans. It's highly likely that the oceans will were we to push the ocean into this horrible place where calcium carbonate shells are impossible, I believe there would be silicon-based life forms as there appear to have been between 55 million and 44 million years ago. So I'm not telling you that the oceans will die, I'm just telling you they'll look profoundly different than they have for the last 44 million years, which in my book is equally worrying. How soon is this going to happen? I simply don't know. It might be 300 years from now if we keep burning every molecule of fossil fuel on the planet. Sadly, it could be sooner. We may soon push the world's oceans into regimes where coral reefs are all but impossible to grow, perhaps through a combination of ocean acidity and heat and the amount of pollution we're dumping into the Great Barrier Reef and the Caribbean and other factors. A combination of stresses might lead to the last remaining coral reefs on the planet simply not growing anymore. As we change the temperature of the oceans, it may be that coral reefs will start to grow in places where they haven't grown. So again, it's hard to say whether we're going to kill coral reefs or simply move them unnaturally around the planet. But again, this is an experiment that I, for one, simply don't want to take part in. There's a very important paper that came out in September 2005 in Nature by, one of the authors was Richard Mateer, who used to work with me in Hobart in CSIRO. And it was really Richard who drew my attention to this problem in 2003 and 2004. And as time has gone on, I've only become more and more concerned. So this is a shell from a live pteropod which has been asked to live not in the oceans as we know and love it today, but in an ocean with a lower pH or a higher concentration of hydrogen ions. And they just don't grow very well. And you can see in this paper and many subsequent papers what happens to that. For the chemists in the audience, there's a wonderful effect from the calcite aragonite equilibrium, which you normally see in limestone caves, but which we will soon exhibit in the world's oceans. Okay, so that's one problem, ocean acidity, and I think if you hang around Scripps in this aquarium over the next year or so, you'll have the opportunity to hear from real experts on this question of ocean acidity. I want to move on and talk to you a little bit more about sea level rise, because it was actually one of the things that generated a lot of controversy, I think unfairly, but it did generate controversy. You might say, Cheryl, is there any such thing as fair controversy? But it's like those live satellite feeds. This is an issue that featured prominently in the response to the IPCC report, so I thought we might take a minute to go through it patiently. This is data on sea level rise from another fellow who used to work with me, John Church, who I think is an outstanding scientist, one of the world leaders in understanding sea level rise. And what he's done is analyzed all of the data that he can find, starting with tide gauges and moving up until present day. And then there's a kind of a 11-year or 15-year record of altimeters, satellites that NASA used to launch before its mission was changed to go back to lifeless rocks in the planetary system. When they were still doing good stuff, they used to help us do Earth science, and they gave very important data, which is absolutely vital to the prosecution of a research institution like ours. And those tide gauges and the satellite data agree precisely. The gray bars are a measure of the inherent uncertainty, and you may ask why that was greater in 1850 than it is now. It's just that the instruments weren't as good. The people that were doing the measurements were drunk more often in 1850, and we weren't collecting as much data around the world, the different tide gauges around the system. So it's important to emphasize that scientists have become more sober in the last 150 years. What's interesting about this data is that John Church had the fortitude to fit not a linear line through this graph, but a quadratic line, which is shown by the blue curve. What Church and White argue in this paper and a number of other papers, including a wonderful paper that analyzed the flat regions of this curve and how they correspond to large emissions from volcanoes, they were able to argue convincingly that there's in fact an increase in the rate of increase of sea level. Again, not in the right direction if you own real estate at La Jolla Shores or in Louisiana. The other important observation that Church made in a paper with a couple of our very own scientists, Ralph Keeling and Richard Somerville, that appeared the day before the IPCC first report came out on the 1st of February this year, is that while the record of IPCC's predictions has been right in the middle of observed trends in the history of IPCC, the one thing that they underestimated was sea level rise. And I'd like to just talk to you for a minute about why that might be. So the reason why it's somewhat difficult to talk about sea level rise is that there are a couple of different contributions to sea level rise, only one of which do we understand well. And I need to explain to you a little bit about how IPCC works in order to explain this. IPCC, as I said, doesn't do research, it analyzes research. It tries to summarize research that's already been done. And in order to do that in a logical way, you actually have to have a cutoff date. You have to say, I'm going to look at all of the papers that are published in the refereed literature prior to a particular date. And the date that the current round of IPCC chose was the end of December 2005. And I assure you that that has to be done. Otherwise, you go halfway through your analysis and somebody says in November of 2006, but wait, this paper just came out. So you have to all agree, you have to all read the same 952 papers, figure out what they mean, and assess them in some logical way. Then send out a draft report, get 30,000 comments back on that, respond to each one of those in a logged fashion, so that there's really some kind of scientific assessment that's done on that. So by the end of that date, only one of these two contributions was well understood, and so IPCC correctly, in my view, said, although not everybody read it, that they weren't going to look at the other contribution from sea level rise. Okay, so the part we understand is of concern enough, and that is that because we're heating the planet up, the thermal expansion of the ocean raises the sea level. This is probably one of the most fundamental material properties. Most things expand when they get hot. Most metals do that. There are only very few materials that actually do the opposite, and they're very important in technology. So, that's not an elegant or exciting part of the problem, but it's important because we're heating up the planet, the atmosphere, the land, and the ocean, and so the simple thermal expansion of the ocean causes the sea level to rise. Of course, in heating up the planet, we're also causing some of the ice to melt. So those two factors put together are what we call in the profession the boring part of sea level rise, and that amounts to 12 inches over the next 25 or 30 years, and that in itself is of concern enough. Because the beaches are flat objects, a vertical rise of 12 inches is many dozens or hundreds of yards in the horizontal direction for most low-lying places in the world, certainly in Bangladesh and Louisiana and other developing countries. The extreme and, dare I say, fun part of sea level rise, although that's a fairly perverted view of the world, is the part that we don't understand. Or I would say the part that we've understood in alarming detail since December 2005. And therefore, all of these great papers that were coming out were not part of the IPCC report. We used to think that we only had to worry about glaciers when they melted. And that's the part that's included in the boring part. It became very apparent in the last 2 years that we have another thing to keep us awake at night, and that is glaciers that are currently sitting on land, so whose volume has not been displaced, Archimedes in the bathtub style, by sitting in water. These are glaciers that are grounded on land that might, at some point in the future, although we don't know when exactly, might slip into the ocean and rise sea level far beyond the 12 inches that we understand well. Now, I hear you ask, when will this happen? And the answer is we don't know. And so the reason that I think you'll see Scripps invest more in this area is that we need to know. We don't know enough about glacial dynamics and how the interface between rock and ice is lubricated by melting water to know when this might happen. We think it's going to happen sometime. That's not very helpful. But it's the same kind of event of, when is the big earthquake going to happen? When is a big asteroid going to slam into planet Earth? We know these things are theoretically possible, but we don't know exactly when they're going to happen. We don't know if there's a 1 in 10,000 chance of it happening in the next 5 years or a 1 in a million chance. And so, unlike earthquakes, we think we have a big chance of understanding more about the probability of these hopefully rare events by doing more science. So let me just try to summarize for you in a couple of words the kind of research that you'll see, and I think over the next year you'll have one of the real experts from Scripps stand in front of you and talk more about this. So here's another one of these graphics that tries to summarize all the things that are happening in the cryosphere. Remember, the cryosphere is a combination of things. So glaciers and ice caps shrinking, the ice caps are shrinking at an increased rate and contributing about 0.8 of a millimeter per year to sea level rise in the year 1991 to 2004. Frozen ground. Permafrost is warming and the active layer is thickening. The active layer is the layer that changes during the annual cycle. So deep down in Siberia, the ground used to be frozen all the way through the year, and what scientists have measured is that the boundary between the annual thaw and the permanently frozen ice has been moving upwards at a great rate. Seasonally frozen ground has decreased in its maximum extent by 7% since 1900. That means that the top layers that used to be frozen in the winter are no longer being frozen. You see that in Alaska too. That's why you see some buildings that, or pipelines or railways that used to be sitting on permanently frozen ground or ice are now sagging under the weight. Snow cover. There's been a reduction of 5% in the period 1988 to 2004, the annual average area compared with the 1967-87 average. And in lake and river ice, the annual duration has been reduced by 12 days over the last 150 years. I could go on, but all of these measurements put together show that there is behavior of the cryosphere, the ice in our planet, that's not only consistent with a warming planet and a warming ocean and a warming atmosphere, but probably exceeding our worst fears. And believe me, we have some bad fears, so exceeding our worst fears is serious. So what the IPCC report was to talk about the part of the sea level rise problem that we understand, and it deliberately said that it wasn't going to look at the dramatic side of sea level rise. So that's the difference between the part we understand is, something that might cause our oceans to rise 12 inches in the next 30 to 50 years versus a dramatic event like things in Antarctica and Greenland sliding into the ocean, and that might cause a 20-foot rise in the ocean. Let me go into that in a little more detail. So I often get asked, who should I believe? Should I believe the Al Gore movie where he talks about the possibility of a 20-foot sea level rise, or should I believe the IPCC report for 2007? And the answer, of course, is believe both. Okay, so here is a little more discussion on ice in our planet, and think of this as a kind of a preview of coming attractions to a full discussion of this. A little bit, I guess you'll hear on July 9th at the next one of these talks, and then over the next 12 months I'm sure we'll be hearing more about it. So the action in this business is going to be found at the boundaries between the ice and other parts of our planet. And there are basically 4 of those boundaries. One that we'll focus on is where the ice meets the ocean. So that means where the ice slides off Antarctica or Greenland, where it's on land, stretches out for a while over the ocean, and then starts to carve out icebergs. So this is often a good sign that something is happening to the cryosphere when you see these glaciers changing in a profound way. There's a boundary between the ice and ocean, such as found in a place like McMurdo Sound in Antarctica, where I used to work. And the reason that that's important is because it gives a potentially warming ocean direct access to the ice. So the ice is very cold. If it comes in contact with salty water that's at an increasingly warm temperature, then the ice itself can be melted at an increasing rate. There's another boundary between ice and rock, such as that's shown here. And there's a fourth interface, the base of the ice streams, where fast-flowing ice comes in contact with fast-flowing meltwater. So what I mean by that is that there can sometimes be a liquid layer between this solid ice and the solid rock. And that's something that we need to understand because it can lubricate the moving of those glaciers. So let me just show you a few slides that try to quantify some of those statements. This is a graph I got from Jeff Severinghouse that shows that the glaciers are shrinking. So these are the sum of data from a bunch of glaciers in these continents, normalized to 1950, and what I'm measuring here is the length of the glacier compared to its length in 1950. So you see that before 1950, these glaciers were longer, in some cases up to 1,200 meters longer than they were in 1950. And you see since 1950, we see by and large a decrease in the length of the world's glaciers. So this is not one glacier, and it's not a measurement of volume. It's a very simple metric that we can all agree upon, and there's no doubt about it that over the last 50, 80 years, the length of glaciers has been decreasing greatly. Now, if you go into our exhibit in the first room here, you can see a lot of photographs. Here are some more glaciers. This is a particular one that one of our students is studying here at Scripps. You can see where the terminus was in 1980. You can see this, for a reference, you can see these little mountains here. So this is where the terminus was, where the icebergs are carving off. And now you can see where the terminus is today. It's way out here someplace. So this is an ice sheet that's started to flow very rapidly. It's now flowing at 25 meters a day. That's 75 feet a day or more. And so this is not an ice sheet that's just gently ambling towards the ocean. It's rocketing off these mountains and into our oceans. So the kind of glaciers that we're particularly concerned about are the ones that have accumulated their ice over many hundreds and thousands and tens of thousands of years. So these ice glaciers develop by the very tiny amount of snow that, there's almost no precipitation in Antarctica. It just, once it falls, it seems to blow around for an eternity. Eventually it gets incorporated into these ice rivers that flow relatively rapidly to the exterior of the continent and eventually break off and form icebergs. What we've become concerned about in the last few years is these melted parts of glaciers. This is a picture from Greenland, but I'll certainly show you in a minute some satellite images from Antarctica, where there's a lot more melting of the surface of these glaciers than we thought. But these meltwater doesn't just sit harmlessly on the top of the glaciers and refreeze in the winter. It plummets through these caverns and eventually makes its way, in many cases, to the interface between rock and ice. And therefore it makes it easy for these glaciers to start moving and perhaps slip into the ocean. I'm going to skip through some of these slides here, but just to show you that there's lots of data. This is not some scientist making it up. Here's the Greenland ice mass that's been measured by satellite measurements between when the satellite was launched and just after 2000 until recently. That's making a discernible change in sea level just from that one phenomenon alone. And here is a pretty profound image of a glacier that's flowing in from the right here. So this is coming down from the mountains, starting in the right. And in 1992, the boundary between the glacier permanently associated with ice flow and the place where it was carving off icebergs and place where the sea would refreeze during the winter was down here. 8 years later it was here, 2 years later it was here, 1 year later it was here, another year later it's back up here. This is what we call in the business rapid melting. So we have the data, and we think we understand what it means. What it means is that liquid water that was formerly tied up above sea level on land, is flowing into our ocean at an increasing rate. We believe that it's associated with global warming. We believe the mechanism for that global warming is from CO2 and other greenhouse gases. Again, I don't regard this as controversial science. This is simple deductions and measurements. I'm going to skip through some of these other slides so we have time for questions. I did want to show you this image of the famous Larsen B ice shelf. This was satellite photography that was analyzed subsequently. This ice, which was always floating ice, so this is the famous Larsen B ice shelf that suddenly disintegrated over a period of a week or so, and generated this many tons of ice that was formerly in a solid, although floating on sea form, simply disintegrated into ice that's floating around in the ocean. Now, of itself, it didn't raise sea level, but what it was doing was holding up the flow of this ice, these ice shelves here, which are on land in these mountains in Antarctica. And what's happened since this ice sheet disintegrated is that these ice rivers in Antarctica have started to flow more quickly. So the effect on sea level, I mean, this is a dramatic effect in its own right. We think that these stripes here, we know these stripes here are just like that slide in Greenland. These are meltwater on the surface of the glacier that, unbeknownst to us, penetrated all the way through to the ocean surface, and then suddenly the ocean state was such that it caused this whole ice sheet to fracture of this many square kilometers. And so since then, since March 5th, 2002, we've noticed a dramatic increase in the ice on land. This, by the way, is why we need satellites looking at planet Earth. So all of these things put together lead me to the reason why Scripps is going to be analyzing these effects increasingly over the next couple of years. It seems that we understand the boring part of sea level rise quite accurately, but there are a couple of factors conspiring together to lead us to believe that the rate of sea level rise is faster than we first guessed, and that there are serious, although perhaps low probability events that could cause much more dramatic sea level rise. And so if you continue to come to this series of lectures, I'm sure you'll hear more about that. And so that concludes my talk, and I'd be very happy to take your questions. Okay, who's first? Yeah, sure. I'll repeat the question for you. We know that there have been changes in the Earth's climate in the past that were clearly not from human intervention. Why do we think human intervention is causing this climate change? It's a great question, and thank you for it. We understand the changes, say, over the last 650,000 years, basically by eccentricities in the Earth's orbit. So there's a wobble in the Earth's orbit, and there's other kinds of irregularities in the orbit. And so that period of glaciation and interglacial periods basically corresponds to well understood phenomena in the Earth's orbit. And during those periods, there's a change in the Earth's temperature and a change in the Earth's CO2 concentration. But that doesn't mean that that's the only way of changing the Earth's climate, and we in human beings have invented and discovered at least one more, and that is by ramping up the concentration of CO2 to levels that we haven't seen in recent geological history. So it's important to emphasize that we now understand in great detail two ways of changing the Earth's climate. One of them is that natural oscillation that comes from eccentricities in the Earth's orbit, and the second one is by us increasing the CO2 concentration from 280 parts per million to 380 parts per million. And the reason we know it's us is just quantum mechanics. We know that CO2 traps heat. We know more CO2 traps more heat. Thanks for the question. Yes? The question is, what can we do? What can we do is stop trapping so much heat in the Earth, and I'm glad you asked, so I've got a few modest suggestions here, and your check is in the mail. I think the most important thing you can do is vote. I really do. I think the statement of the scientific problem is so overwhelmingly agreed upon that it now requires a whole breed of politicians, not just in our country but all over the world, who are going to operate on a time scale of 10 to 15 years. And that's a challenge because we're used to solving community problems on an electoral time scale, which is 2 years or 4 years or 6 years if you're in the Senate. But when people say to me, what can I do? The most important thing is to vote. And I don't care which party you vote for, but I hope you'll look at the candidates' positions on climate change. I do think you have an opportunity to do something pretty profound every time you buy a house. Now, for some of us, as we move around the world, that's sadly a frequent, painful thing to do. For others of us, if you're lucky enough to live in the same beautiful house for 30 or 40 years, it's not an opportunity. But there are many things that you can do when you buy a house. You can look for a house that's conveniently located to your work or to public transportation, as I had the opportunity to do. Or you can look for an energy efficient house that's just big enough for you and your family and no bigger. There's a lot you can do next time you buy a car. Again, it's, some of us get, sadly, to do it quite frequently. One of my wonderful staff had her car wiped out by a wayward driver a couple of weeks ago, and she went out and bought a hybrid car, just as I did. In our local area, I think there is something that we can do, and that is to campaign for the trolley to come from Old Town to UCSD. When you think about our wonderful undergraduate students, sadly we don't yet have housing for more than about a third of them on campus. They commute from other parts of town. I think we could have a huge impact just locally if the trolley, which is already, people have agreed to build in 2016, if we just did it by 2009, I think we can have a real impact on the amount of traffic and the amount of parking we need to build on this campus. I think we can do a lot in solar energy. My friends in Israel tell me they get 80% of their hot water from efficient solar collectors. It's not new technology, it's technology that's existed for a long time. I think in California, in the west and south of America, we could easily do more with existing solar technology. And one of our friends and big supporters of Scripps Institution of Oceanography told me that she had looked at the amount of heat that she'd dumped into her swimming pool in the last 30 years and measured that with the 3 times that she'd actually used the pool and felt some regret. So if you have the opportunity, if you're lucky enough to have a pool, you might want to look at your heating bills. So just off the top of my head, that's some actions that we can all take, and they're probably in order of importance. Thank you very much. I hope you enjoyed the talk.